Alright, welcome to the last part of the partial derivatives, and now we're going to talk about taking higher derivatives. So we're taking, the second partial derivative. So after taking the first partial derivatives, we're talking about, okay, what can you do after that? And so there's a few things that can happen after you take the first partial derivative. So we'll talk about the first. So say you take the partial derivative with respect to x. Alright, so right there. Then you want to take it again with respect to x. So you're taking the second partial derivative of x, and you're doing it twice. And so the way to denote that is throughout all these ways to denote it, okay? Now I want to highlight a few of these. So here's how the notation is going to be for the most part, the partial derivative of xx. That first sub is the first partial derivative you took. So f sub x, f of sub x means that's the first thing you did. You took the partial derivative with respect to x, and then you're going to do it again. All right. Now, the notation, the Leibniz notation is over here, right? Where whatever you take the partial derivative of first is actually going to pop up second. So you took the partial derivative with respect of x first, and then you're going to take the partial derivative with respect of x again. Now, if you really can't tell the difference when you're taking it at the same variable, but notice when we're doing, okay, let's take the partial, let's look at this one. The partial derivative of x, y, means that we took the partial derivative of x first and then y. Notice that x appears first and then y. So we took the partial derivative of x, then we took the partial derivative of y. But in the Leibniz notation, we're taking, we took the partial derivative of x first and then y. Notice that what we take the partial derivative of first is going to appear on the far right. What we do second is going to appear on the left. All right, so it's kind of, reverse intuitive. We're used to reading things from left to right, but in the Leibniz notation, we're taking partial derivative. We're taking it of, trying to turn that alarm off. We're taking it of, when we're reading this, at the Leibniz notation, it's kind of reading right to left, as opposed to left to right when we're looking at kind of like the Newton notation. All right, so just keep that in mind as you're seeing these written out, because it does matter, so a lot of times it does matter what came first. But one thing that I wanted to note as well, too, is that when you're taking the partial of x, then y, and then if you're taking the partial of y, then x, if we're doing those two variables, then what you should notice that you should always get the same thing. All right, and we'll explain more about that in the next section. Not next section meaning the next set of notes. So here's just reiterating the notation of what comes first, what comes second. So find all second partial derivatives. So what we want to do is we want to first find, okay, what's partial of x and what's partial of y, and then we'll find, all the other partial derivatives. So let's take our partial with respect to x first. So we have sine of 2 mx plus 9y. And so it's going to be 2 sine of mx plus ny times cosine mx plus ny times the derivative of the mx, and that's just going to be m. All right. I'm going to rewrite this. So I'm going to go ahead and make sure that you see the identity of the double angle formula. So if I have sine of 2 theta, that's just 2 sine theta cosine theta. So I'm going to kind of do the reciprocal of that, and I'm going to have 2m not 2m, just m. And then I'm going to have sine, I don't need that parenthesis, m sine of 2mx plus 2ny. Alright, and I'm able to do that just using the identity, and same thing for partial f of y. I'm going to have 2 sine mx plus ny times cosine mx plus ny, but times n, and so I'm going to have n sine of 2mx plus 2ny. Alright, so now let's take the second partial derivative of x. And so we first took it with x, and now we're going to do it with x again. And so we have m on the outside. Derivative of sine is cosine, so cosine of 2mx plus 2ny. And taking this with derivative of x, so times 2m. So we're just left with 2m squared cosine of 2mx plus 2ny. Again, you didn't have to use the identity, but taking the second partial derivative would have been more of a pain. So now let's take the second partial of xy. So still I'm working with x, but now I'm going to take the partial derivative of this with respect to y. And so I get m cosine of 2mx plus 2ny times 2n, the derivative of the inside with respect to y. And so now I'm left with 2mn cosine 2mx plus 2ny. Alright, now let's do the same thing, but now let's do it with taking the derivative. We took the root of y first and then x. So now we're working down there and taking the derivative of that with respect to x. And so I'm going to have n, derivative of sine is cosine, so cosine 2mx plus 2ny. Then taking the derivative of the inside with respect to x, so 2m, and I get 2mn cosine of 2mx. Hold on, there's too many parentheses that I put down. So cosine of 2mx plus 2ny. And notice that the partial of xy and the partial of yx, they're going to be the same, all right? So you really don't have to do that twice. Now, it's a good way to check, but again, you don't have to do it twice. And so now we're doing the second derivative of y, of yy. And so now we're just going to use the second f sub y, and we're going to take the derivative of that with respect to y again. So we're going to have n cosine of 2mx plus 2ny times the derivative of 2ny, so it's just going to be 2n. So we're going to have 2n squared cosine of 2mx plus 2ny. And there are all of our second partial derivatives. All right. Clause's theorem. So suppose f is defined on a disk D that contains points A, B if the functions f of xy and f of yx are both continuous on D. Then what Clause's theorem is saying is that if you take the second partial derivative doing xy and then yx, they're going to be the same value. So basically what I was saying up here, Clause's theorem is these are always going to be the same. Again, you can check, so you don't really need to do it once because they're going to be the same. So like if you did f sub xy, you could just say here f sub y x, and you're like, okay, that way you wouldn't even have to work on this one, because you can say, oh, hey, they're going to be the same value. So that's the the two partial derivatives, right? But I'm just going to show both because I want you to see that they always are going to equal each other if it's continuous and if you did your work correctly. All right, so now last one, we want to find the indicated partial derivative, and here we have three independent variables. And so notice how it's written g sub rst. So when I'm trying to find the indicated partial derivatives, as in this case it's the third partial derivative, I need to make sure that I'm going in the right order that it wants. All right, since this is written as g sub rst, the first partial derivative that it took was g sub r. So we're going to go ahead and find that. So taking the derivative of our function e to the r sine st, the derivative of e to the r is just going to be e to the r sine of st. Right? So really nothing changed there. Now let's take the derivative of grs. So now using g sub r, let's take the derivative of that with respect to s. I'm so mad at that alarm. Alright, so we have e to the r sine of st, and taking the derivative of that, so e to the r, derivative of sine is just going to be cosine st. Derivative of the inside with respect to s is just going to be t. So we'll just put the t in front, and we're finished there. Alright, and now all we need to do is take the derivative of grst, which is fun because now we have the product rule. So taking the derivative of t is going to be just e to the r, derivative of the first times the second, cosine st, plus derivative of the second. Derivative of cosine st is really just going to be minus sine of st. So let's go ahead and that minus sine of st times the derivative of the inside with respect to t sub s. We'll have st e to the r. And if we want to, we could pull out an e to the r. Since it's the end of the notes, I'll do that. And we'll just have cosine st minus st sine of st. Again, you didn't have to pull out that